Algebra 2, we're finally moving away from sine and cosine and going into tangent. Of course, tangent equals sine over cosine, but still, we're moving into tangent. First of all, I pulled some stuff out of my textbook as a reminder to tell you. And what I want to tell you, I'll underline in red. So, tan of x plus pi equals tan x is not an identity. So today we're talking about identities and what we're going to do with tangent. But the statement tan x plus pi equals tan x, as long as x is not equal to pi over 2 or any combination of pi over 2 as you rotate. I'll erase this in a second. But pi over 2 is up here. So x cannot be pi over 2 or 3 pi over 2. Or, as we keep on going back and forth, it can't be pi over 2 plus any combination of pi for integers of k. That's an identity. So I wanted to make sure that I reminded you of that. Tan is not valid at pi over 2 because the cosine function. So we have tan equals sine over cosine. Up here at pi over 2, cosine is 0, and you're not allowed to divide by 0. It's undefined. Can't do it. So that's why. But let me erase all that. Let's see, what else did I want to tell you? Oh, this lesson uses both x and theta to represent the independent variables for the tangent function. I thought it was interesting that x is used when working with a circle, the unit circle. Sorry, did I say x? That's hilarious. Theta is used when working with a circle, and x when we're working with the xy plane. I just thought it was interesting. Let's see. Theta is a set of all real numbers. It can't be 90 plus 180k, which is the same as pi over 2 plus k pi. Those are equal. Oh, which we have right here. So, summary. Let's try something else and look at this unit circle for a second. If I say that tan theta equals sine theta over cosine theta, looking at the unit circle, and this right here, I should have made that a little bigger, says x theta, y theta. I can actually express this tan theta in terms, we have sine of, we have SOHCAHTOA. Sine is opposite over hypotenuse, so if we have theta, we have opposite over hypotenuse, and it's the unit circle. Hypotenuse is always 1, so we're just going to say sine of y sub theta, and cosine, which is x sub theta. And let's not confuse you, and we actually don't have to put, oh no, I can't erase my sine. We don't have to put sine in there at all, because sine of theta is y sub theta over 1, and cosine of theta is x sub theta over 1, which is why tangent of theta is y sub theta over x sub theta. Phew. Cool. Alrighty, let's move on. Okay, you have like gobs and gobs of tables to fill out in your classwork. I've done a few of them for you. Actually, let me add in a slide. Hold on a second. Here is an answer to groups 1 through 4, and the next slide will be groups 5 through 8. What the curriculum wants us to do is together in class break into 8 groups, which is sort of hard with us. Hand out a copy of the axis and a table, and use a calculator to generate approximate values of the tangent function in the tables below. Each group would create a graph of just your portion of the tangent function, and then we could put all those graphs together to make one big graph, but we can't do that. So here's the table for group 1 through 4, and the next slide will be group 5 through 8. I don't need you to fill this in. Your calculator will approximate all these values for you. Make sure your calculator is in degrees versus radians. Here we would be in radians just to get the right value. But I'm going to fast forward now and go back to those graphs that I created, and let's talk about them. Here's that second, groups 5 through 8, if you want to look at it. Notice they're all the same, all of them. And each group is going through a different range on our graph. You know, if I had a long graph, where actually each section goes through different parts of, pi, repeating constantly. So, here we have from -2.5 to -3, -2 pi over 2 to -3 pi over 2. Sorry, this would be negative. Let's get it straight. -5 pi over 2 to -3 pi over 2. Here we have +5 pi to +7 pi, etc. So we have lots of different parts of our graph, which I will show you in a minute. But the important part is, look, it repeats. Okay, different parts of our XY coordinate, they're just going to repeat over and over again, and I'll show you why. And here we go. So, the group that I have put in here, we have group 1 is in green. We went from -pi over 2 to pi over 2, and then group 2 is in black. We went from pi over 2 to 3 pi over 2. And then what did I do next? I think I did group 4, which is in blue. Now I did these all in Desmos. I set up a table, and I can show you how to do that if you don't remember. But I just set up a table and I plugged in all of the x values and all the tan x values, which I put in for y, and graphed them. And as you can see, our tangent function repeats. It's a periodic function, but it has sort of an issue with it. If we remember, I'll write it down here, tan x equals sine x over, I should do theta since we're doing a unit circle. Tan theta equals sine theta over cosine theta. It's undefined at pi over 2 plus k pi. So we actually have an asymptote at each pi over 2 repeating. So what we have here is our tangent function increases, but it will not go past, it just approaches pi over 2. It goes away from -pi over 2 and approaches pi over 2, repeating. Okay, it will never cross that asymptote line. And it just repeats over and over and over again. It's sort of complicated to put these graphs into your graphing calculator. You have to get your window set just right so that you can see your asymptotes and you can see your graph, which is why Desmos was just easier for me to use at this point, and I can copy and paste it into my slide. But that's really the point in this exercise, which means if you did groups 1 through 8, you would get 8 iterations of this tangent function graphed, all between the asymptotes given. All right, I think that's it. This is everything. I already copied the actual answers for you, though. And showing you sort of blow up of each thing. What happens to the graph near the edges of your interval? I typed this in because I thought it would get a little messy if I tried to write it. So go ahead, oh goodness. Let's go ahead and read it. Near the edges of the interval, x approaches a value where the tangent function is undefined. That's our asymptote. Since cosine pi over 2, cosine of pi over 2 plus k pi equals 0 for any integer k, the tangent is undefined at the edges of the interval we are graphing. As x gets near the edges of the interval, sine x gets close to either 1 or negative 1, and cosine x gets close to 0. So tan x equals sine x over cosine x gets very far from 0, either in the positive or the negative direction. We have asymptotes. Okay, it's a line that will not cross at pi over 2. Or 3 pi over 2. Or 5 pi over 2, etc. Okay, negative pi over 2. It's our asymptote. It's pretty cool, but something we need to take into account. Something else I'd like to bring up, that this is pi over 2. We always go through 0 at pi, 0, 2 pi, and at pi over 4, that's when we hit 1, which is about right here. At pi over 4, y equals 1, which you can see on your table. It's sort of hard to see, so if we have negative pi over 4, my scale is not right for this one and I can't change it. At negative pi over 2, y equals negative 1. So as we're graphing these, and we have to graph a lot of them for homework, first thing I did is draw my x and y axis, separated into pi and 2 pi, and then pi over 2, because that's my asymptote. And then I would do pi over 4 and negative pi over 4, 1, negative 1, and those are my dots. So we go through 0, 1, negative 1, and I can sketch pretty well. Okay, I'll do it again and a bigger piece of a slide. Okay, exploratory challenge 2, exercises 6 through 16. Yes, that's a 16. Whew. This is a discovery exercise, and we're going to talk about many facts or identities about the tangent function using unit circle with the slope interpretation. If you remember, we've done in the past, tangent equals slope of a line. I think we just did it in the last lesson, or we've done it in geometry. They're getting confused in my head now. So tan equals sine over cosine, which is y over x, which is slope. So as we graph y equals tan x, that's what we're going to discover is our slope. So for each exercise below, let m equal tan theta, our slope, be the slope of the terminal ray in the definition of the tangent function, and let p equals xy. Sorry, my phone rang. Be the intersection of the terminal ray with the unit circle after being rotated by theta radians for between 0 and pi over 2. We know the tangent of theta is the slope, m, of line OP. So first of all, let Q be the intersection of the terminal ray with the unit circle after being rotated by theta plus pi radians. So we have our terminal ray. And kindergarten just walked by. Goodness. So what I was saying is we have our terminal ray, theta degrees, so our line goes between theta and then theta plus pi. So here, right here is theta again. So what is the slope of line OQ? If we have points P, O, and Q that are collinear, that means they share a line, the slope of OQ is the same as the slope of OP. So we have the slope of OP, which is tangent of theta, is the same as the slope of OQ and PQ because they are all collinear. Let's write it down. The slope of line OQ is the same as the slope of line OP because they're collinear. Therefore, the slope of line OQ is also m. Find an expression for tan of theta plus pi in terms of m. Well, tan of theta plus pi equals m because tan theta plus pi is the same as, tan theta plus pi is the same as tan of theta, and the tangent of any line is equal to its slope. Okay, find an expression for tan theta plus pi in terms of tan theta. Well, we just said tan theta equals m, so if I'm going to find an expression in terms of tan theta, there we go. I can just interchange those two. How can the expression in part C be seen in the graph of the tangent function? Well, the pieces of the tangent function repeat every pi units because tan theta plus pi is equal to tan theta. So it's periodic, it just repeats. Well, let me write that down for you. So that's what we just said. The pieces of the tangent function repeat every pi units because tan theta plus pi is equal to tan, not pi, tan theta. Okay, moving on to number 7. So now we know why the period for the tangent function is pi and not 2 pi. Because we constructed quite a few of them. Well, I only constructed 3, but in class we would have constructed 8 that repeat every pi. But so let's try to see if we can connect that into more unit circle information and more slopes. So let's get into it. Let Q be the intersection of the terminal ray with the unit circle after being rotated negative theta radians. So we're rotating the same distance backwards, which is sort of a reflection over the x-axis, but that's okay. Let's look at it. So part A, what is the slope of line OQ? So ray OQ is a reflection of ray OP across the x-axis. So we have coordinates of Q would be just x theta comma negative y theta. So the slope of OQ is the opposite of the slope of OP. So if we have the slope of OP, if we have that as m, the slope of OQ would be the opposite, or negative m. And we could calculate it using those values of x, y, and x negative y. We're going to get the same answer. So find an expression for tan negative theta in terms of m. Well, we just said it's negative m. Moving on, find an expression for tan of negative theta in terms of tan theta. So tan of negative theta equals negative tan theta. So negative m, and m is tan of theta, so you can take the negative to the outside. How can the expression in part C be seen in the graph of the tangent function? So the graph of the tangent function does have rotational symmetry about the origin. So we just rotated it about the origin theta degrees. Let's write that down. Okay, that's what I just said written down, so pause and copy if you'd like to. Number 8, is the tangent function an even function, an odd function, or neither? How can you tell your answer is correct from the graph of the tangent function? First of all, let's just look at what we said about the information. We said in number 7 that tan of negative theta equals negative tan theta. That means that we're odd, okay? If the graph of the tangent function is rotated a whole 180 or pi radians about the origin there will be no change in the graph, because we've said that your slope stays the same if you rotate a full pi or a full 180 degrees. Okay, for some reason I didn't copy down the actual problem on this one. It says let Q be the intersection of the terminal ray with the unit circle after being rotated pi minus radian degrees. Or sorry, pi minus theta radians. I can't use radian and degree in the same sentence. So if we see on this picture, it looks like that right there is theta, but we're talking about pi minus theta degrees. So I could continue this on here. That was my alarm. And we would have theta here also. So what is the slope of this? A little bit harder to figure out, but we know that ray OQ is the reflection over the y-axis. So the coordinates of Q are negative x, y. So the slope of OQ, change in y over change in x, is the opposite of the slope of OP. So we're at negative m. So find an expression for tan of pi minus theta in terms of m. Well, just like the last one, oops. Pi minus theta equals negative m. And then tan of pi minus theta equals negative tan of theta. Cool. Let Q be the intersection of the terminal ray with the unit circle after being rotated by pi over 2 plus theta radians. We're getting more complicated now, aren't we? So if you look, here's theta. That means right here is also theta, if that helps you sort of picture what we're doing here. So let's answer some questions. What is the slope of OQ? And remember, slope equals tangent, right? So ray OQ is the rotation of ray OP by 90 degrees. Counterclockwise, yep. So line OQ is perpendicular. We have line OQ is perpendicular to OP. What do we know about slopes when they are perpendicular? Yes, opposite reciprocal. So the slope of OQ is opposite sign reciprocal of the slope of OP. Find an expression for tan pi over 2 plus theta in terms of m. And then find an expression for tan of pi over 2 plus theta in terms of tan theta, and then in terms of cotangent theta. So we're going to say this is equal to, let's put it down there, negative 1 over m, which is tan, which is equal to negative cotangent theta. I don't know why I wrote cosine. There we go. Cotangent theta. Very fun. Number 11, let Q be the intersection of the terminal ray with the unit circle after being rotated pi over 2 minus minus theta radians. So excuse me, if this is theta, that means this is also theta. So for this one, ray OQ, I don't know, I'm in red, sorry. Ray OQ is the reflection. This one's always hard to figure out, but it's the reflection of ray OP across the line y equals x, which I'll draw in there. Not very well. Y equals x cuts that in equal parts. So if you looked at it, the coordinates of Q are yx. Yes, I did those backwards, but that's the coordinates of Q. And the slope of OQ (1 over m). So if you did that calculation, the slope is 1 over m. Find the expression for tan pi over 2 minus theta. It's 1 over m. And then keeping with our pattern, tan pi over 2 minus theta equals 1 over tan equals cotan. Okay, let's summarize what we've done. Hold on a second. Okay, this is what we did for all of those exercises. Let's just summarize it. So tan of theta plus pi is the same as tan of theta. So remember, plus pi. Tan of negative theta is negative tan of theta. That was when we said that everything is odd. Tan of pi minus theta. So we have pi minus theta. That's when we went down here. And then pi over 2 plus theta. So we're adding 90 degrees to it. That gives us 1 over tan theta. Make sure that's negative, which equals negative cotan theta. And then pi over 2 minus theta gives us 1 over tan theta, which is the same as cotan theta. Okay, this is what we learned. We're going to graph these on an xy plane, which will help us remember them a little bit better too. Okay, we've only demonstrated that the identities in exercise 12 are valid for theta between 0 and 90 degrees because we only used rotations that left the point P in the first quadrant. So our terminal ray ended in the first quadrant. Argue that tan of negative 2/3 pi or 2 pi over 3 is equal to negative tan 2 pi over 3. So tangent of negative 2 pi over 3 is equal to negative tangent of 2 pi over 3. Then, using similar logic, we could argue that all of the above identities, all the identities in number 12, extend to any value of theta for which the tangent and the cotangent, for the last two, is defined. So let's go through the thought process in that. Hold on a second. Okay, let's talk through this. First of all, I drew an xy plane, and I looked at the degrees, well, the radians. I changed it into degrees for 2 pi over 3. So right here we have tan of negative 2 pi over 3. So I drew in black negative 2 pi over 3, which is negative 120. So here is my terminal ray. For this particular degree, I have tan of theta. I'm looking at my slope is the square root of 3, which is 1.7, I think, 3. Therefore, I can say the tan of negative 2 pi over 3 equals positive square root of 3. In red, you'll see here I have positive 120. So tan of theta, which is my slope, is actually negative square root of 3. This is a negative slope here, which is negative 1.73. So tan of theta equals my slope of my terminal ray is negative square root of 3. Tan of 120, that's a positive angle measurement, equals negative square root of 3. So what we just said right here, or what the book is saying, that tan of negative 2 pi over 3 equals negative tan of 2 pi over 3. Now let's continue with the problem. So using similar logic, we could argue that all of the above identities extend to any value of theta for which the tangent and cotangent is defined. I need another slide to continue on the explanation. So write this down if you can. I'm moving to a new slide. Okay, so to continue on, we can say that because the terminal ray of the rotation for negative 2 pi over 3 is collinear, shares a line with the terminal ray for pi over 3. Guess what? Pi over 3 plus 2 pi over 3 equals pi, 180. Collinear. We can say that tangent of pi over 3 equals tangent of negative 2 pi over 3. Okay? So to continue that just a little bit, we can also say that tangent of negative 2 pi over 3 equals negative tangent 2 pi over 3. Chew on that for a little bit. Next question. For which values of theta are the identities in exercise 12 valid? Okay, exercise 12 was a few slides ago. So we can show that the value of theta can be any real number that does not hold on a second. Number. A little bit better. Okay, that does not cause a 0 in the denominator. That's where we get our asymptotes. The tangent function is only defined, and we've said this a few times now, for theta cannot equal k over 2, pi over 2, plus k pi. For all integers k. We've said that quite a few times, though. Because tangent is sine over cosine, basically we talk about cotangent, which is cosine over sine. Let's just make sure that we know that theta cannot equal pi k, or k pi. Cool. Number 15, derive an identity for tan 2 pi plus theta. Okay, what does that mean? 2 pi, so I have pi, 2 pi, and back to the beginning. Because the terminal ray for rotation of 2 pi plus theta and the terminal ray for rotation by theta coincide, so a rotation of 2 pi plus theta is equal to a rotation of theta. We see that tan of 2 pi plus theta equals tan of theta. And the same restrictions apply. The same restrictions apply. And number 16, use the identities you summarized in exercise 12 to show that tan 2 pi minus theta equals negative tan theta. Okay, I'm going to go back to, I looked at exercise 9, so go back and look at exercise 9 yourself. Page back. You've written it down too. It says that tan pi minus theta equals negative slope equals negative tan theta. That's what exercise 9 says. Now let's look at exercise 16. I have tan 2 pi minus theta, which I can break that up into pi plus pi minus theta. Now you'll see that I've got equal things going on here. Equals tan pi minus theta equals tan negative theta. So what did we just do? The problem we're looking at, I broke it up into tan pi plus pi minus theta, which that's 2 pi. We set up here tan of pi minus theta, we know. So if we look at just tan of pi, drew myself a little picture here. Pi is 180, tan is y over x. At 180, y is 0, x is 1, so tan of pi is 0. So now you can just look at tan of pi minus theta. And we said in exercise 9 that tan of pi minus theta is the same as tan of negative theta. Okay, from exercise, I think 7, let me go look. Yep, from exercise 7, we proved that tan of negative theta equals negative tan of theta. So we can solidly say that tan 2 pi minus theta equals negative tan theta for all of the same restrictions. Okay, we just did a little proof and it made sense and we're happy. Good job. So our lesson summary, these are the whole shebang. Okay, that's everything that we did this lesson. It was a lot. Once we get to our problem set, we're going to be graphing these a lot. So I will scan in my answer key and send it to you if you want to start your problem set now. And if I haven't done that for you yet, just shoot me a quick email. I've got it all saved. I can shoot it to you really quick. Cool? Good work today.